This video is a review of the ideas of ratio and proportion, which is discussed in your text in sections 7.1 and 7-2. What makes this witch's shoes look so real? As we can see, there are some people walking by the shoes, and the people are smaller than the shoes. And since we know that in real life a person has to be much, much bigger than a real shoe, what is it that convinces us that these shoes look real? Well, it's the way that the artist constructed them using proper ratio and proportion. For example, the measurement from the toe to the ball of the foot must be in proportion to the measurement of the entire shoe. That must be in the same proportion as it is in a real shoe, and that's what helps convince us that these look like shoes. Artists have long known the importance of ratio and proportion. For example, what if I were to try to convince you that this person here, being the shorter of these two people, must be a child, and this must be an adult, because it's the taller person? Well, you wouldn't believe me, because this picture simply looks like a baby, and we may not know what makes it look like a baby, but we know that this looks like the baby, and this looks like the adult. Here we have a chart of one reason why that's the case. For a baby, the head is about 1/4, 25% of its entire height. And for an adult, the head only takes up about 6% of the person's entire height. So this is how an artist can give us a clue as to the age of a cartoon character, even when we don't know what size that cartoon character is actually meant to be. Okay, so which triangle looks like a good scale model of triangle A? Triangle B or triangle C? If you said triangle B, that's probably because you somehow intuitively knew that the ratio of this leg of the triangle to this leg was the same as the ratio of this leg to this leg. I'm calling them legs because these are both right triangles. And we can put some numbers into that to prove it. We have 2 boxes wide here along the base of this triangle, so we have 2 units. And the height of the triangle is 4 units. For this triangle, the base is 1 unit and the height is 2 units. So we could set up a ratio or proportion that says 2 is to 4 as 1 is to 2. And since 2 is half of 4 and 1 is half of 2, we can see that this is true, which is what makes this triangle look like a good scale model of this triangle. So in math, we have several different ways to express this kind of proportional relationship. This first way that we just discussed is read kind of like an analogy. An analogy of A to B is the same as C is to D. But more commonly in math, we write proportional relationships this way. And it might seem strange to you at first that we made a proportion here into a fraction here. So in this way of writing it, A was 2 and B was 4. So in writing it this way, we would say 2 over 4, or 2/4. Since C was 1 and D was 2, we would say 2/4 equals 1 over 2. And by simplifying this fraction, dividing top and bottom by 2, we can see that indeed this statement is true. 1/2 equals 1/2. Now, here's perhaps an even more unfamiliar way of expressing a proportional relationship. AD equals BC, meaning A times D equals B times C. Well, let's see if it's true in this case with these numbers. Our A is 2, so we have 2 times, or D was 2. And on the other side of the equal sign, we have B was 4 and c was 1. So this equation turns into 4 equals 4, which is also true. How can we explain that this strange way of writing a proportion actually turns out to express the same relationship that we expressed over here and over here with fractions? Well, you might have heard of this before as cross-multiplying. And instead of just cross-multiplying here for you, I'm going to actually justify why that works. So in algebra, as you know, we can multiply both sides of an equation by the same thing. I'm going to multiply both sides by d, and then this d is going to cancel out with that d. So what I have now is, since this is d over 1, I have dA over b equals c. Now I'm going to multiply both sides of this equation by b, which is the same as b over 1. So I have c times b over here. Now this b is going to cancel, and I have dA over 1 is just the same as saying dA equals cb, which is the same as bc. So you can see that the math works out to turn into this equation over here. The way that you might be more used to seeing it done is a over b equals c over d, and someone might have told you, look, you can just cross multiply. So bc goes on this side of the equal sign, and AD goes on this side. Be careful, because cross-multiplying frequently gets misused. Oftentimes, you're asked to simplify an expression like a over b times c over d. And I've been told many times by math students that they should just cross-multiply and say that this is the same as bc over ad, which is simply not true. There was a multiplication sign here, whereas here we have an equal sign. It's also not true that we can take something like this, a over b equals c over d plus, say, x, and just cross multiply and say something like dA equals bc plus x. That is simply not true. The only time that we're allowed to use this trick of cross-multiplying is when we have simply a over b on one side of an equal sign and c over d on the other side. Nothing else. Okay, let's do an example problem that asks us to find the value of x given this ratio or proportional relationship. So here, with great trepidation, I am going to use the word cross-multiply because I have an equal sign here. I have a over b equals c over d. So I am going to say 4 times 5 equals 2 times x, which turns into 20 equals 2x, dividing both sides by 2. That gives me x equals 10. You try this one. Okay, let's do another example. Now you might take a look at this and say, whoa, wait just a second here. I bet we can't use the cross-multiplying trick because look, we have something here that looks more complicated. This doesn't look like a over b anymore. It looks like a plus something over b. And then this does still look like c over d. So what I'm going to tell you is that as long as we treat this entire numerator as one thing, we keep it together as its own thing, we can still treat this like the a that we talked about in the last example. And one way that you might remind yourself to do this is by putting parentheses around it right away, around that whole numerator. And then we can go ahead and use our cross-multiplying trick. So on this side of the equal sign, I have 3 times x plus 3. I'm keeping my parentheses there because x plus 3, the whole thing, was my a. On the other side of the equals, I have 2 times 4. Okay, now this looks like a friendlier problem. I can distribute the 3 inside this parentheses. So I have 3x plus 9 equals 2 times 4, which is 8. Subtracting 9 from both sides, I get 3x equals negative 1, so that x winds up being negative 1/3. You try one like this. Okay, for one last example, I'm going to really throw you because in this example, we have complicated looking expressions in each one of these places, A, B, C, and D. And not only that, but when we cross multiply, we're going to get something that looks a little bit like something you might not be used to. But let's just dive in and try it. So for this cross multiplying step, we can say x minus 1 times x plus 2, the quantity. On the other side of the equal sign, we have x minus 2 times x plus 4. Okay, you might have been taught a method for simplifying an expression like this. Remember the FOIL method? So we're going to multiply the first terms. X times x is the same as x squared. The outer terms, so plus 2x. The inner terms, minus 1x. And then the last terms, which is negative 2, because I have negative 1 times 2. On the other side of the equal sign, I'm going to do the same thing. X squared plus 4x minus 2x minus 8. Okay, this looks like an equation that you don't like to meet every day because it has an x squared in it and a regular x in it. But don't be too panicked because in this case, the x squareds are going to disappear. First, let's combine like terms. I have plus 2x minus 1x. So since those are like terms, they both have an x not to any power besides the first power. So 2 minus 1, that just leaves us with 1x. So I have x squared from here plus x minus 2 equals, I still have x squared on this side, plus 4 and minus 2 gives us plus 2x. And then from here I have minus 8. Okay, now we get to subtract x squared from both sides of the equation, leaving us with no more x squareds in this equation. Because fortunately, we had 1x squared on both sides. So now all we have is x minus 2 equals 2x minus 8. So I'm skipping a couple of algebra steps here. I'm going to be left with x on this side and 6 on this side. And you can check my work there on your own paper. You try this one. For further practice with this, see page 247 of your text, numbers 9 to 19 odd and 33 to 39 odd.